Brady thought that tin was a really boring element, but we've changed his mind, shown him that it does more than it says on the tin. What we're going to show you is how tin melts, how you can join wires on the battlefield while you're being fired at by the enemy, how you can stop things growing on the bottom of ships, and also give you a few hints about our first year chemistry course if you come here to the university. Tin is in group 14, the same group as carbon, so it is below germanium and above lead. It was really valuable in prehistoric times because it was found that when you mix it with copper, you could make bronze, and bronze melts at a lower temperature than copper, so it's easier to make weapons, and the weapons were harder. Tin is found in a variety of minerals. There are large sources of it in China, in Malaysia, and also in Cornwall in the west of England.
After the ore has been crushed and washed, the tin oxide is dried and samples tested for quality. A good sample should yield 140 pounds of tin from a ton of ore.
There are still many abandoned tin mines in Cornwall. They're quite dangerous when you walk across the moors. There are open shafts which, if you're not looking where you're going, you can fall down.
Eventually, Cornwall could provide a third of all the tin required by this country.
We have been trying to look at tin, beginning with the metal. One of the interesting things about tin is that it melts at quite a low temperature. So if you heat it up, it melts around 230 degrees centigrade. So even with a gas torch, you can melt it quite easily in a glass test tube. This low melting point is very useful for a whole series of applications, particularly for so-called solder, that is, joining things electrically. This is solder. It is the metal which is used to make electrical connections, in this case on a very old computer memory board. Now, to make joints like this requires precise tools, and it's a bit boring. But what we want to show you is how people joined wires together on the battlefield, for example, in the Second World War. You've got to imagine you're on the battlefield, people are shooting at you. You need to put down the telephone wires so you can talk to the groups on either side of you. And the last thing you want to do is to get out a soldering iron and wait for it to heat up and so on. I remembered that I had some self-soldering joints, which I got when I was an army cadet, when I was about 15. There's a copper tube with some solder inside and some material that burns so that you can light it like a match. So you take the two bits of electrical wire you want to join, post one piece of wire on each end, and then you light it. The solder is inside. I've had these 56 years, and they weren't new when they got them, so they probably come from the Second World War. They're probably surplus. I thought they would work. Neil was a bit dubious. As usual, I was right. So Neil set fire to the red part, which is some sort of igniting mixture, and it flared up quite quickly, and then you can see the whole tube gets very hot. Now, of course, you can't see the solder because that's inside, but as it gets hot, the solder melts and runs around the wires, and then as it cools down, it solidifies, fixing the wires into this short piece of copper tube. On one occasion, we did it more than once, you could see the solder coming out just on one side. Just to show that the solder was in there, I persuaded Neil and our new assistant, Connor, who's joining our team, to heat one of these pieces vertically so that when the solder melts, it will drop out to the bottom. Just to show you that it got hot, we put a thermocouple, which measures temperature, into the top, so you can see the temperature going up and you can see the solder running out. So we were really quite excited. Then we thought, tin is in the same group as carbon. Carbon burns, so perhaps tin will burn well in a Bunsen. We found some very nice, finely powdered tin. Neil started sprinkling the tin into the flame of the Bunsen burner, and it was really beautiful. You could see all sorts of swirling flames. And when the tin went into the flame, you got quite a bright coloured light. Now, there's some argument whether it was violet or lilac, and that there was a touch of green as well, which I think came off his spatula. It was really much more beautiful than any of us had expected. And then Neil had a really good idea. He fed the powder into the air hole of the Bunsen burner. The stream of gas then blew the powder up into the flame, and that looked even better. So we'd had two really good experiments, demonstrations, and so we felt really ready to go for a third. Now, tin is very well known of having two different forms of the metal. One of them is shiny and looks just like any other metal. The other one is meant to be a sort of brownish colour and crumbles away. This transition between the two happens at low temperature. And I'd seen a terrific time-lapse video on YouTube where you can see a block of metallic tin gradually crumbling away as this so-called tin pest spreads across. So we thought we would try the same, but perhaps we were not quite so patient. So first of all, I had a nice tin soldier, and we tried dunking the soldier in liquid nitrogen. It came out looking much the same, but we hoped it had transformed inside. So Neil thumped it with a hammer. That was successful. It shattered to bits, but there was absolutely no evidence that the metal had changed. It was just Neil's power that smashed it. So we then tried a different experiment, melting the tin and pouring the molten tin, the liquid tin, into liquid nitrogen. The thinking here was that if we froze the liquid quickly, it would go into the unstable form directly without going through the metallic one. So it was really quite spectacular. When it went in, there were great plumes of vapor, water vapor, as the nitrogen evaporated. And when we took it out, it was a rather beautiful shape of long piece of tin. But it was the shape of the test tube, so it looked quite artistic, but it didn't demonstrate what we wanted. We thought perhaps we were being a bit impatient, so we left it in liquid nitrogen overnight on a piece of string in case it crumbled away. And sadly, when we took it out the next day, still hadn't transformed. For once, we've been completely unsuccessful. I think that when we've done it at too low a temperature, you probably need it a bit below freezing point of water, so -10, -20 degrees centigrade, And when it's really cold, liquid nitrogen temperature, the atoms don't have enough thermal energy to rearrange. If we left it in liquid nitrogen for a couple of years, perhaps something would happen. So as well as bronze, there's a very well-known alloy of tin called pewter. Originally it was tin and lead. It's now tin with other metals. It's particularly famous in Malaysia. You get many souvenirs. And when I was in Malaysia, I was given this plate made out of pewter. And the reason why people like it is because you can melt it quite easily and make it into elaborate shapes like the pattern on this plate. Now, we really haven't talked about the chemistry yet. Tin is in the same group as carbon, so it has 4 electrons in the outer shell. But unlike carbon, it can either use 2 of these electrons or 4 of these electrons for bonding. When it uses 2 electrons, it forms, say, tin dichloride, stannous chloride, which is a salt, rather like sodium chloride. So it dissolves in water, makes a slightly cloudy mixture if you put too much in, but it dissolves. But it will not dissolve in organic solvents like cyclohexane. On the other hand, if you use 4 electrons, you can make compounds like tin tetraiodide, which is one of the compounds our students make in the first year lab. And we had 2 samples made by students, and you can see the colors are a bit different because one made a purer sample than the other. The tin tetraiodide is like an organic compound. If you put this one in water, the tin iodine bonds react with the water, so you get hydrogen iodide, which you can't see, and you get a precipitate of tin oxide, which is white. If you put it in an organic solvent, it dissolves, so you get a nice yellow solution. I won't say any more, or you might cheat when you're a student here. Tin oxides are important in screens on smartphones and similar things because this display consists of a material which is sandwiched between 2 electrodes. And obviously the electrode through which you're looking has to be transparent. And indium tin oxide, that's a mixed oxide of indium and tin, is electrically conducting but is transparent. So indium tin oxide is a key component of most smartphones and other displays. So if you're watching this, you're probably watching it through a thin film of indium tin oxide. The final application of tin that I want to tell you about involves ships. This is a wooden ship, but it's the only one I could find. When a ship is made, obviously the bottom of the ship is absolutely clean. But as it sails around the seas, various marine organisms, mussels, barnacles, and so on, fix themselves to the bottom of the ship and start growing. So eventually, the bottom of the ship looks rather like my hair, covered in these marine organisms, and this greatly slows down the ship. It doesn't go through the water so easily. So for centuries, people have tried different sorts of coating on the bottom of ships for so-called anti-fouling to stop organisms growing on them. A very successful method is involved using organo-tin compounds, usually derivatives of tributyl tin. These are very effective in preventing growth on the bottom of the ship. The problem is that the tin can leach, dissolve off the bottom of the ship, and particularly near ports, because there are a lot of ships there and they spend quite a lot of the time there. And when the tin comes out, of course, it stops the organisms, the barnacles, fixing onto rocks and all sorts of things. So in recent years, there's been quite a strong movement to stop using tin in anti-fouling paints and to use clever paint chemistry to make the bottom so smooth that nothing can stick to it.
There you go, and to think I thought a video about tin would be boring. As you probably know, we've made videos about all the elements on the periodic table, but like the one you just watched then, we're redoing them, making them bigger and better. If you'd like to support us, help us make those new videos, like the people whose names you see on the screen at the moment, You can back us on Patreon. Go to patreon.com/periodicvideos. Patreon supporters occasionally get little extra goodies. For example, I'm about to share with them this video about the Professor's tie collection. You haven't lived until you've seen a video about the Professor's tie collection. Anyway, there are links down in the video description. Thank you so much for watching, and we'll be back soon.